All right, so I created this as separate videos because we're gonna kind of switch gears here. And we're gonna talk about something called dummy variables or indicator or binary variables. So suppose we've got a regression. Instead of a nice continuous variable for X or Y, one of them is just ones and zeros, right? So it's binary or it's a dummy variable. So the examples of this would be if I had, an observation for all of this, let's assume I'm going to try to predict, I don't know, let's say for this one, I'm going to try to predict income. And I might think there's might be some gender disparities in income. And so my Y variable is income, my X variable is, are they male or not? Well, that male variable is only a one every time the observation is from a male, zero if it's not. I could use an identifier for one if the person was over 60, zero if not. If I was trying to predict SAT scores from whether or not they were student athlete, a one every time I had a student athlete in the observation or in my data set, zero every time that they're not. So our linear regression equation will look exactly the same. I'm just going to use slightly different notation, which is that our X variable is now this dummy variable, right? So our slope coefficient, we're going to interpret it a little bit differently, and it's going to have slightly different implications when we're thinking about what the predicted Y values are. So in general, we said the interpretation of our slope coefficient was the predicted increase or decrease in Y from a 1 unit change in that X or independent variable. So our units now, if it's a dummy variable, a 1 unit increase would be going from the zero to the one group. So if I think about having like my student athlete variable and SAT as my Y, it would be the predicted change in SAT scores from going from being not a student athlete to being a student athlete, going from the zero to the one group. Okay. So we can do the same three hypothesis tests, right? Right, left, two-tailed. Now we're always going to do, just like for the continuous variables, a two-tailed test where we assume that there is no effect or that the relationship between that dummy variable and our Y variable is zero. Right? So the assumption is really the same. Our test statistic, we calculate it really the same way. It's just we're looking at the coefficient on a dummy variable. This is always zero. So it's really just take that slope coefficient estimate we see from Stata and divide it by the standard error that Stata has calculated for us as well. Okay. So the steps, I literally copy and pasted this from what we went through the first time. It's the same exact steps as what we would do if it was a continuous variable. We've got this null and alternative, which is always that we assume that slope coefficient estimate is equal to zero. We've got our three benchmark alphas of 0.1, 0.05, 0.01. We can find our critical value, calculate our test statistic using simply taking the slope coefficient estimate dividing by the standard error, since this is always zero. We could then compare the test statistic. Is it in the rejection region? We reject. We could also use our test statistic to find the p-value. If the p-value is less than alpha, we reject. Or we could look at the confidence interval, and if it includes zero, we fail to reject, and if it doesn't include zero, we would reject that assumed true value of zero. So everything applies the same. So here I did have, it wasn't SAT scores, it was college GPAs and whether or not they were a student athlete in college. So I ran this regression. Notice here, it's significant. I've got a p-value of zero. That's going to be less than any alpha that we look at, 0.1, 0.05, 0.01. So at every single level of confidence, kind of benchmark level of confidence, we can reject the null that there's no relationship between being a student athlete and their GPA. And in fact, how would we interpret this coefficient? Well, remember, a 1 unit change in a dummy variable is going from the zero to the one group. So going from being not a student athlete to being a student athlete would predict that your GPA falls by to what? 0.28 points, right? And then how do I come up with that test statistic? I simply take my coefficient estimate of negative 0.28 and I divide it by that standard error of 0.048, which gives me this negative 0.59. Also notice, so I'm kind of showing you walking through us. So this would be clearly in the rejection region. Remember, our standard normal kind of benchmark values for critical values are 1.65 positive and negative, positive negative 1.96, and positive negative 2.58 that correspond to those alphas of 0.1, 0.05, and 0.01. We also can see that our confidence interval does not include zero, which means that if we do a hypothesis test for the value of zero, we would reject it. So all three of those things, using the test statistic comparing to the critical values, comparing our p-value to alphas, or looking at our confidence interval at the 95% level, we could reject using all of those, right? They should all lead to the same rejection decision. So let's think a little bit harder about what the meaning of this dummy variable would be if it's a dummy variable that's our independent variable. So let's say I had height, right? And I was trying to predict height using this dummy variable of male. Okay. So I think I've got this in the slides, but I'll kind of work through this here. So let's say I've got height and this dummy variable of male. Right? If I wanted to predict the average height, so this is a very simple linear regression, but the average height for someone who's female, how would I come up with, if I had these estimates, how could I come up with my predicted height? Well, if they're female, this variable would be equal to 0. So for females, my predicted height from a very simple linear regression would simply be the intercept. Right? Now, if I wanted to make a prediction for a male's height, this variable becomes a 1. Anything times 1 is itself. So the predicted height for males would be the intercept coefficient plus that slope coefficient on the dummy variable. So if we're thinking about graphically, and I chose height because we kind of know just some biological truths that if I'm looking at, and this will get kind of weird, but if I'm thinking about like male and kind of predicted height here, when male is 0, the predicted height is my intercept. If male is 1, the predicted height would be the intercept plus that coefficient, right? So this difference would really be that coefficient on my dummy variable. Or what would the change in predicted height be if I went from the 0 group to the 1 group? Okay. So that's what we're doing with dummy variables. It really is just picking up differences and kind of where that average predicted y value is going to start out at. So there we go. So I kind of have that in here, just slightly different. It's really representing the difference in my group's means. Now, we'll talk about what happens when we combine. We don't just have one variable on the right-hand side, but for now, we're just thinking about if I just were to predict this simple linear regression using just a dummy variable on the right-hand side as an independent variable, it's just telling me about the differences in the average height of my 0 group relative to my 1 group, right? That coefficient is the difference, okay? So I kind of already talked about this on the other slide. In terms of what that effect is, we said that when they are a student athlete, we would predict that their GPAs are about 0.28 lower. But we could also think about if they're not a student athlete, what would their predicted GPA be? Well, just that intercept coefficient or just the constant. So if they're not a student athlete, their GPA is approximately 2.67. If they are a student athlete, it's about 0.28 points lower, or what? 2.39, if I'm doing math in my head correct there. Okay. All right. Also, just to point out some things that we've talked about already relating to like last class, is this simple linear regression something I should really be relying a lot on? Well, what percent of the variation in GPAs can I explain by just the fact that they're a student athlete? I would look at my R squared. It's 0.008. Remember, the R squared that we're reported is always in terms of like a proportion. So if we're thinking about percentages, that would be what? Move the decimal 2 places. So we're only explaining 0.8% of the variation in GPAs with student athletes, which means we're not explaining what, 99.2%. There's probably a lot of other things that are better predictors of GPA than whether or not they're a student athlete. However, student athlete does have a statistically significant effect, and 0.28 would probably be economically significant as well, because I mean, GPAs are measured usually on a 4-point scale. So that's not a small effect, right? So what if instead, so that was if we had a dummy variable as our independent variable, right? That told us the differences in kind of the means of those two groups, the 0 and the 1 group. What if I have a dependent variable as my, sorry, what if I have a dummy variable as my dependent variable, the y variable? So what would the units of my y variable be, right? So let's think of another example. Let's see, do I have one here? Yeah, let's skip ahead. I'll come back to this. Let's say I have the unemployment rate in a county, and I have a dummy variable as my y, or dependent variable, which is it a metro county or not? So inherently, we might think, well, metro areas, in the city tend to have higher unemployment rates. Well, maybe, maybe not, right? We can kind of test that, right? That would be my initial inclination. Maybe it's wrong. So how do I interpret a slope coefficient? It's a 1 unit change in my x variable. So here, if the unemployment rate is measured in percentages, it would be a 1% increase in the unemployment rate, would change the predicted y value by beta 1. So if this dummy variable goes down by 0.045, what is that really saying? Well, if a dummy variable is only between 0 and 1, the units of my y variable are essentially changes in the probability it's a metro county. So if I were to select a county at random and its unemployment rate goes up by 1%, the probability that it's a metro county would decrease by 0.045. Oh, there you go, 0.045. Okay. So a 1% increase in my unemployment rate decreases the probability of belonging to that one group, or in this case, decreases the probability of being a metro county by whatever my slope coefficient estimate is associated with that x variable. Okay, so that's how we interpret our slope coefficient when we have a dummy dependent or y variable. Its changes in that y variable represent changes in the probability we belong to the one group. And I say the one group, the group that would be coded as a one, right? Being a metro county. So this actually goes against what I thought, because this is telling me that when the unemployment rate is higher, it's actually less likely that I'm going to be looking at a metro county. So this is saying the unemployment rates in rural counties must be higher, right? So because, if unemployment rates being higher means it's less likely to be a metro county, that means that when unemployment rates are higher, it's more likely it's a non-metro or a rural county. Okay. I skipped this to give you an example because it's sometimes easier to talk through an example. But in general, right, the way I interpret this slope coefficient is it's the expected increase in or decrease in the probability that, it's an expected increase or decrease in the probability that that y value is 1. So let's look at another example here. Oh, wait, what do I want here? Oh, I've got another example in Stata, which we'll switch over to in a second. Let's now think about, what about the intercept coefficient? How would I interpret that? Well, remember, the way that I interpret the intercept or the constant is when the x variable is equal to 0, that's the predicted probability, or predicted value of our y variable. So if the unemployment rate in a county is 0, the predicted probability it's a metro county is 0.6. So if the unemployment rate is 0, the predicted probability I'm looking at a metro county would be whatever that intercept coefficient is, which is 0.6 here. Right. Okay, we're okay with that for right now. So let me make sure here. I think I've got some other stuff. We already talked about this. Oh, where was I at? Simple linear regression, causation. So I think my next slide I'm gonna hold off on. We'll kind of revisit this. But what I wanted to look at instead is going through some examples in Stata, right? So let me make sure I'm sharing. Oh, let me make sure I'm sharing the right screen with you. There we go. So I'm gonna have to open up this data set. So let me use my file path. Well, we're gonna use that data set we were using on Tuesday. So my COVID county data. Then we're going to go down here, and this was going to be what we run through for class 2. So let's use one where I've got a dummy variable for whether or not, so this is what we were looking at, all the county level data, and then the COVID, like how many COVID cases they had, etc. So here I'm going to run a regression, right, using that regress command. On my y variable is the number of new cases, and I forget what year, I think this was in like October 2021. And then a dummy variable for whether or not the county was in the south. So my initial inclination was here thinking, oh, if it's in the south, people are more likely to be outside instead of inside. Maybe we don't have as, much transmission of COVID. So I'm going to run this regression and can kind of look at, okay, what is my slope coefficient on that dummy variable, which was just a 1 if the county was in the south, considered in the south, and I forget what states I included in this. We could look at the data and figure it out, but like, you'll notice here, where's my south variable? Yeah, so it looks like Alabama was in the south, Arkansas, or no, sorry, Alaska wasn't, Arizona, I didn't consider the south. So I don't remember exactly, or did I? Sorry, I'm looking at the Midwest one. Florida was in the south, Connecticut wasn't. So it's just this 1, 0 variable. So how do I interpret this coefficient on my dummy variable? Well, remember, a 1-unit change in my dummy variable is just going from the 0 to the 1 group. So being a county in a state that's considered in the south relative to not, the predicted change in the number of cases actually goes up by 892. So this went against my original kind of what I thought would happen, which is that counties in the south would see lower. Well, maybe this meant that counties in the south, people are out moving around more. It's more likely we're going to see this disease spread. Now, can I reject the null at my conventional levels? I usually default to the p-value because I think it's easier. So notice here, can I reject the null at my 90% confidence level? Well, 90% confidence, I'll kind of show you. I'm not sure if this is something I think I might have did it when we were doing review, but just to kind of reiterate it here, because I use this terminology quite often. So we've got confidence, significance, and alpha. So if I'm doing things, saying things at the 90, 95, 99% confidence levels, that corresponds to 10, 5, and 1% significance. These would be alphas of 0.1, 0.05, and 0.01. So in this example, we had a p-value of exactly 0.01. So is my p-value less than alpha at the 10% significance or 90% confidence level? Yes, so I can reject the 90% level. It's less than 0.05, so I can reject the 95. It's not less, right? It's equal to 0.01 at the 99%, so I would fail to reject with 99% confidence, okay? So notice I rejected at 95% confidence. So what should be true is that that value of 0 is not in my confidence interval. Sure enough, my confidence interval only includes positive values here. It doesn't include 0. So with this dummy variable, we said, what does the intercept coefficient kind of represent? Well, that would be the predicted value of y, number of new cases, when my x variable is equal to 0. So this would be kind of like the average number of cases in a county if it's not in the south. So for all the counties not in the south, the average number of cases was 3,000. If it then was a county in the south, the predicted increase in the number of cases we could expect was about 892. So just more interpretations, kind of getting used to making these. Now, maybe the number of cases, maybe the populations are different in the south. So I said, okay, let's use a different y variable where it's not just the number of cases, it's the number of cases per 1,000 people. So I think I just took cases and divided by the population here. So notice here I'm getting, oh, okay. Now it looks like I can reject, first of all levels, but I still have the same size. Same sign on my slope coefficient, right? That when the county's in the south, I expect a higher number of cases per 1,000 people. So kind of evidence here that being in the south, we saw higher transmission of the disease. Now, what's a better predictor of the number of cases per 1,000 people? Well, if I look at how much of the variation in my y variable was explained by just if the county was in the south, I have to look at my r squared. So my r squared is in proportion form. So 0.178 would be 17.8%. I'm explaining with just whether or not the county was identified as being in the south, 17.8% of the variation that exists in the cases per 1,000 people. If I were instead to run this regression where I try to predict the number of cases by the percent of people vaccinated, Notice it has an R squared of 0.04. Whoa, this is interesting. So the amount of variation in the number of cases per 1,000 people explained by what percent of the county is vaccinated, only 4% is explained, where just being in the South, I can explain 17%. So what would we say is a better predictor if I just had to choose one? Whether or not the county's in the South is actually a better predictor than the percent of the county that's vaccinated. Might go against what we initially thought. Okay. Just to prove this to you, some things I was saying earlier. Remember, I said when we run this regression with a dummy variable as my independent or X variable, the intercept tells me the average or the predicted Y value for the zero group. So counties that aren't in the South, the average expected cases per 1,000 people is 33. For counties in the South, the predicted cases would be that 33.6 plus 15.48, so about what? 49. Those should represent the averages of the zero and the one group. What are some other ways I can do this? Remember, we talked before about this by sort command. So what this will do is it's going to summarize this Y variable by this other variable. Well, this other variable South is only two values. It's 0 or 1. So it's going to tell me, it's going to summarize or give me the mean, is really what we want, because I said this should represent the mean of the zero group. This plus this should represent the mean of the one group. Hopefully I'm seeing these exact same values when I calculate the mean by this South variable. Sure enough, when South is equal to 0, my average is 33.66. And if I look at the mean of the South counties, it's 49.1, which would have been these two coefficients added together. So I'm not telling, I'm trying to prove to you what I'm telling you is not completely, we're supporting this with some data here. Okay. We looked at this example in the slides, so I won't kind of go through this one again. Well, I'll change it here. Let's say, sometimes I do things on the fly. Let's see something that might be interesting here. What's a dummy variable we've got here? So we've got where it's located. I know what I'll do. Let's do, so I'm going to create mean. What do I want? Let's think about, so I'm going to calculate the mean vaccinated. I'm then going to generate I vaccinated, which is going to be equal to a 1 if this statement is true. If the percent of the county that's vaccinated is above the mean of the nation, I'm going to put a 1 in here, 0 if not. Okay. So I'm then going to think about, my Y variable is this new dummy variable. And I think I have household income in here. So what was this median household income? So I'm going to change my X variable to be median household income. So I'm going to think about what this is telling me. So I'm trying to predict whether or not a county had a high percent of its county vaccinated, so above the mean, based off of what the average or median household income was in that county. So this is really telling me that when counties have higher income, were they more or less likely to be, to get a high percent of their county vaccinated, or were wealthier individuals getting vaccinated at higher rates? So I'm going to run this I'm going to run this whole code because I have to create the variable first. Now notice, this is a good one to use as an example because what is the units of my median household income? It's in dollars. So for every $1 increase in the average income of the county, the probability, remember our Y variable being 0 and 1, this coefficient represents changes in our Y variable, which the units are essentially the probability it belongs to the one group. So if my median household income goes up by 1, the probability that it has above the average vaccinated or above average percent of its county vaccinated would go up by, well, this is a weird number. So sometimes when we have really small coefficients, Stata is going to show us this kind of scientific notation. All this means is times 10 to the -6. So this means move the decimal 6 places to the left. So 0.000009. So if I have a $1 increase in the additional income in a county, sorry, in the median household income in a county, it would increase the probability that it's considered a high vaccinated county by 0.0009. Well, that's really small, but I could always scale this up to saying, well, what would if I had 1,000 additional dollars of average income in the county? Well, then it would increase by whatever the effect of $1 was times 1,000. So sometimes we'll have really small coefficients because the units of our X variable are going to be small. And if we think about probabilities, well, what's the largest probability increase we could see? Going from 0 to 1, so 1. So our coefficients when we have a dependent dummy variable are usually going to be relatively small because changes in the probability of 0.01, I mean, that's a 1% change, right? So when we use a dependent variable that's a dummy variable, we can expect to probably see some smaller values, okay? We won't go through this example. This is just an additional one if you want to go through it, or we have a dependent or not a dependent dummy variable, but an independent. We've already done quite a few. Here's kind of the next topic, so I'm going to hold off on that. But we're using things we've already talked about, creating dummy variables or using existing dummy variables, and then running regressions where we have a dependent dummy variable or we have an independent dummy variable and making kind of the interpretations of our slope and intercept coefficients. Okay.